Hello 108 class, Mr. McHugh here with you on our last talking class note videos here. We're going to wrap up page 6. This is the last one for the section, last one for the chapter, last one for the course. So let's go ahead and focus here. Let's try to get through these last couple examples. And this is objective 4 out of the book, and of course everybody knows these are for extra credit. These problems are not necessarily that hard to do. It's just a matter of taking a little bit of time and look at them and discovering some new equations here. And objective 4 talks about base E, exponential growth or decay. And excuse me, I want to bring this up a little bit here. And this happens in real life, real world here. Scenarios of, oops, that's supposed to be the x-axis and that's the y-axis. And things will start off very small, slowly grow. Our human population has followed this, okay, and turns around, and then all of a sudden things start to turn, and that's not the best looking parabola I've ever made in my life, but I'll try another one here. Things come up and they go like that, and you notice you hit that turning point. And I caution everybody about this because we're talking about global warming. Everybody, oh, does it exist or doesn't exist? And so, you know, things are going along, people don't really notice it, and then all of a sudden one day you starts going faster, and then you come up to here and people go, whoa, what's going on? Look at the slope of the line there, okay? The slope in the beginning of this is very small. Look at the slope between this point and this point, very what? Steep. Okay, so exponential functions can sneak up behind you, and then when you hit them you can't turn them off and they keep going. Okay, so enough of my spill on that. I probably would go crazy about talking about global warming or something here. So these examples here, they talk about an equation. Y represents the amount of something, of growth or decay, given based on a function of time. So t is time, and they're going to give you y sub 0 is the coefficient in front of e. It's the amount present at the time 0. Okay, and e is your 2.71 raised to the exponent that's got k as a constant and has to be given to you, and time. Okay, so now example 9 is not in the book. This guide does not match our example 9 in our book, but it illustrates this example up here with growth or decay. And I guess what I really was attracted by when they put this in the old version was hybrid cars from 1999 started. Somebody has predicted that this formula f of x or y based on x's time, okay, you could put t in here if you wanted to, would be 10,014 times e raised to the 0.5761. That's the constant. Okay, they give this to you. Now these problems are pretty easy to do because what you could do is when x equals 0 for the year 2000, that's when they started this. Okay, so then the first question is how many cars were produced back in 2002? So you let x equal 2, again that's time, and you simply take the equation, put the 2 in, you got your calculator, and you got a lot of grinding to do on your calculator. Now help yourself out a little bit, show a couple lines of work. 0.5761 times 2 is 1.1522. Hit your calculator, E to the X button, by the way, to help you out. Put the number in, get that result, multiply by 10,014, and you can see I showed some of the detailed work here. So 3.165 is the result of e to the 1.1522. Multiply them out, and bang! Back in 2002, we had 31,696 cars. That would be interesting to do some research and find out how close this model, this mathematical model, predicted the actual. But I'm with you. I remember when hybrid cars came out there. So the thing I want you to look at is, you know, this happened back in the early 2000s. Hybrid cars, gas prices starting to go crazy. Then they ask you the second part. What do you think? What do you think? How many were produced back in 2010? Well, let x equal 10 to represent that. Stick it in and grind away. Okay, you could follow that plug and chug work, but look at the numbers, look at the analysis. Being a system engineer, I'm always trying to encourage my students, do the trend analysis. Okay, look at that exponential curve, it's going up there. Okay, 3,181,000 in 05. What's been going on? What happened in 05? For me, I moved out west and Hurricane Katrina was coming through. price of gasoline hit $3 for the first time. Okay, it's floated as high as $5 a gallon. We've been at $4 a gallon. Okay, what has that done? It's changed our economy. People are looking for more fuel-efficient vehicles. It's hampered our economy. We've had a recession because when the price of fuel goes up, everything else associated with it. You turn around when gas is $5 a gallon, you order a pizza, and they want to give you a surcharge on the gas for the pizza to be delivered. So, just a small example of the impacts of all that. Okay, so those aren't too bad. Now, example 10 here in my notes, let me help a little correlation here, is in the book, it is example number 9. Okay, and it's the exact same problem. So, this is dealing with half-life of carbon-14. It's carbon dating. You probably have heard this. They find ancient discoveries of bones, and we try to find our ancestors who have been around for millions of years. Carbon-14 is the radioactive decay, and they use this equation. The amount Y equals Y sub O is the initial amount times E raised to the negative 0.000121 times T, and again that T is time. Okay, so this example is right out of the book here, so you can follow along there on, I forgot to tell you the page 618. Okay, so if the initial amount of carbon-14 is 10 grams, after 3,000 years go by, how much would you have left of carbon-14, the Y? Okay, so good news is that's on the left-hand side of the equation. This is a plug-and-chug problem. You put 10 in, that's part of the equation, or excuse me, it was given to us, 10 grams. E raised to the negative 0.000121 times 3,000 years. Okay, now I did not do all the nitty-gritty details. You got your calculator. Double check your answers. You should come up with 6.96 grams are left. So you start off with 10 grams. You go 3,000 years, and you've got about 7 grams left. Okay, I'm rounding here. Okay, so those problems aren't too bad. Now what's interesting is equation B turns around and asks us, what would the half-life be for that 10 grams? How long would it take it to go from 10 grams to 5 grams? Okay, and so what you're going to do is take your equation, and instead of putting my dogs are barking. Okay, shh, excuse me. Hey, Gizzy, knock it off. Sorry, the last video, the last 2 minutes, and my dog's become famous. Yay, Cheyenne. Excuse me one second, I have to yell at my dogs. I'll try to cover it up. Knock it off, you 2, 3. Okay, sorry. They've been slugs all day, and then they get all excited because a car goes by. Yay. So, example B, how long for half-life? You put 5 in, okay? There's your equation, E raised to the negative 0.000121 T. We're going to solve for T. Okay, now how do we do that? I divided both sides by 10. Divide both sides by 10. I got 0.5 equals E to the negative. I'm tired of saying it. You got it. Now I come up here. What you're going to do, you see E, you need to take the natural log on both sides. So the natural log of 0.5 equals the natural log of E to the negative 0.00121 T. Okay, that's a key step there. Now, next step, bring down the T. Natural log of E is 1. Don't forget that. So you've got 1 raised to the, anything raised to an exponent is that exponent. So you get 0.00121 T. Divide both sides by that, and you find out your final answer is 5,728 years for that carbon-14 to go from 10 grams to 5 grams is over 5728 years. That's what that problem told you. Okay, these are kind of like, I don't know, you see these problems in physics problems, I think, here, or chemistry problems, they might cover them. So, hey, we've done it. Class, if you get any more details there, check the book on page 618 there. They'll show you some of the nitty-gritty details if you get lost. But it's fairly straightforward problem there. Okay, class, I just want to take a moment. I just want to thank everybody for being patient with me. For my summer online 108 class, You'll Always Be Special as Plank Owners is my first class to go through these talking class note videos. I've had a few of my students have gone through most of them, so I appreciate that. Any of your comments you have, like I've said before on page 4, please tell me in your send me emails, class evaluations, things we're doing. Just let me know. It is the class where it is today, and the success I've had is from students' inputs. I call it the good, bad, and the ugly, and I've tried hard here to make this online, so you got to know me as best I can. It's been a challenge for everybody. I hope these have been a resource that have helped out. So with that said, Mr. McHugh, finally, after many hours of making talking class videos and you guys watching, it is a wrap. We are done, and I commend you and I give you kudos again for all your efforts and outstanding efforts this summer. So I'm probably going to make a couple whiteboard videos here if we go through the rest of the semester, so you'll probably see a little bit of me there. So that's it. Time to say goodnight, Irene. Turn out the lights. Okay, take care. Bye.